probably think the sooner the better too, so. Welcome everybody to another Biostatistics lecture series. Today our presenter is Sergey Tarima, and he'll be talking about ANOVA. And as you'll notice on the evaluation sheet, there is a disclosure on the back. If you need an evaluation sheet, please raise your hand and I'll run around and give them to you. You will need to fill it out for a CME credit if that is what you're interested for. And if you didn't get a handout, please raise your hand and I'll come around and give that to you too.
Thank you everybody for oh, it works. Thank you everybody for coming to this lecture. I'm always feel a little bit nervous when I start a lecture or something, or recitation, whatever. So today we will be talking about ANOVA and how to compare more than two treatments. So essentially we can talk not only about treatments, we can talk about any parameters which are measurable and how different distributions and specifically means of these parameters between different groups. Okay? Go down. Okay, so I believe this is a mandatory slide here that I have no financial interest. Let me go ahead. Okay. So in outline of this lecture will be the following. First, I will talk a little bit about a regular two-group Ttest, which you probably know, but we just have some refreshment about it. But after that, when we, because ANOVA is a generalization of a Ttest on more than two groups. So Ttest applied for compare two groups, ANOVA when we have more than two groups. And the problem of Ttests, because if we have several groups, how we would be applying them? On pairwise basis between different groups or how? So, and we will highlight this point and we'll be talking about multiple comparisons, just a little bit. After that, we will talk about one-way ANOVA. In one-way ANOVA, we have only one factor, which partitions, which splits our population into groups, versus two-way ANOVA. We will touch a little bit two-way ANOVA, where we have two different factors, which generate different partitions of our population which you want to make inference about. Okay, so Ttest. Suppose we have just two groups, okay? And my daughter, she's in 5th grade, so this example was pretty close to me. I thought, okay, suppose we have two classes, okay? In first class, so teacher is Mr. First, and in second class it would be Miss Second. So what we want to compare? We want to compare mean responses between those groups. Mean responses of what? And here we need to specify what we will be comparing between two groups. For example, we will be comparing number of target slips. Suppose yearly number of target slips for each person. Suppose in Mr. First class we have like 16 students, and Miss Second we have like 18 students, right? So, and for each student we can calculate how many times the student was late for a class in a previous year. Okay, so and this number can be obtained and it will be our measurement. Okay, so it will be measured for every student in a class. And when we perform Ttest, we usually make assumptions. And assumptions, we assume that our data came from a normal distribution, from normal populations. So, let me go ahead. What does it mean, normally distributed? So, you already visited several similar lectures before, and I believe normal distributions was already covered. And you remember when we talk about a bell-shaped distribution? So in this case, we're talking about a normal distribution. But the problem is, not all distributions are normal. And moreover, it's a pretty rare situation when we really have a normal distribution, when our data really normally distributed. So, and here I just made this example up. So suppose in Mr. First class, we have the following data. So first student had only one tardy slip, second student had 10 tardy slips, across the whole year, and so on and so forth. Okay? In the second, we also have some data. So, and in total, we have 16 students in first class and 18 students in second class. Okay? So, if we want to compare those two classes, we can perform Ttest. And Ttest will compare just means between those two classes, just mean number of target sleeps. Okay. So if our data would be normal, in this case, what we can do, we can calculate two numbers for every class. We can calculate sample mean, so we just average across all target sleeps, right, in first class, and standard deviation, which shows variability around this mean. And similarly, for second class, we can also calculate mean, which is just an average, and standard deviation. If we use these two parameters, just mean and standard deviation, so in this case, we can approximately describe how our data are distributed within two classes. And here I just put I'll give you an example how our data would look like if we would use only those two parameters, only means and standard deviations. Okay? But not necessarily our data look like that. And this is what we will see. This is how our data really look like in first class. Okay? So you remember we had several zeros in our first data set for first class. And by the way, we know that all our data, they are positive or zero, right? 0, 1, 2, and so on and so forth. So actually, we're talking about discrete data because we never saw like 1.5 target sleeps and so on. This is a histogram, right? And this histogram says that, for example, in this part we have 0 and 1. If you lump those two events together, so we have in total 5 events in our sample. If we go back, okay, so we should see 5 times 0 or 1s. 1, 2, 3, 4. Maybe I changed my data a little bit. I'm sorry. Weird. Okay, so probably I changed my data a little bit. Okay, so these data do not look normal. Okay. If you look at second class, our data are not normal again. So we don't have this bell-shaped curve which is supposed to be seen here. And as I mentioned, these histograms show that our data are not normal. This means that our data cannot be fully described by those two parameters which I mentioned to you before. So it's mean and standard deviation. But at the same time, the nice part about Ttest is that when we have a lot of data, we can summarize this data in forms of different statistics. And one of these statistics is just means, right? So we can calculate mean number of target sleeps for one class, mean number of target sleeps for second class. We can calculate the smallest number of target sleeps in every of these classes. All of those are statistics. And statistics, they highlight different aspects of our distribution of our data. And what Ttest does, Ttest compares means between two groups. Okay? If means are different, so in this case we can detect it with our Ttest. At the same time, if our data are not fully described by those two parameters, it means that even though our statistics are the same, suppose means in our classes are the same, it doesn't mean that distributions are the same in our classes. Okay? So, but Ttest still eligible for comparing two means. And moreover, when I talk about normal distribution, that our data should be normally distributed, well, in statistics there is a nice theorem which actually assures us that if we have pretty large sample size, then these statistics more or less are normally distributed. And usually, if we see like we have 30 or so subjects in every group, so in this case we know that we still can use Ttest, we still can use ANOVA, and in this case we will be able to compare means in our groups. So, T-test allow to compare means between two groups, and as I mentioned, 30 subjects per group is usually sufficient to be able to apply T-test. Oh, I already mentioned several times without data not normal. Okay. So, and here are those two statistics. So if you look at first class, if you calculate mean, just sample mean, so this is what we would do. We would add up all our numbers, divide them by total number of subjects we had in our first class, and we will get mean. So it's about 6 tardy sleep on average in Mr. First class. If you look at second group, in second group we can also estimate the same mean, and we can again estimate standard deviation. So what we can see in this case, in second group mean is 8.3. So on average, we can say that a little bit more tardy sleeps per person in second class, and variability is actually a little bit higher, because variability, which is described by standard deviation, so in this case how our number of tardy sleeps jumping up and down around our mean, class mean. So we can see that this variability is smaller for first class, whereas for second class, standard deviation is a little bit higher. Okay. Two-sample T-test. So what I presented here, this is what statisticians usually see. When we run our statistical analysis, I usually use R or SAS for that purposes. Here we have just two-sample T-test from R program. Okay, and you're probably not interested in all that part. The only part you're actually interested in the p-value, because p-value is used for making our decision, for making our statistical inference. If our p-value below some cutoff point, so in this case we can say that we, and here statisticians usually pretty careful, we fail to reject the null hypothesis of no difference, okay? Because what our null hypothesis in this case that means, I mean those two groups are the same. Mean number of tardy sleeps in this particular example, okay? So we are not accepting this null hypothesis in this case. We just, we are not, by the way, maybe, okay, so 5%, this is our cutoff value. So if this value, 26, is greater than 0.5, in this case we fail to reject our null hypothesis. So we are not accepting it. So we are not claiming that we have the same number of tardy sleeps on average within each of those two groups. We just fail to reject it. Okay? And on the opposite, if our p-value is suddenly below 5%, so in this case we say, okay, our groups mean number of tardy sleeps are different between our two groups. So, and what is the meaning for this 5%? Because 5% is actually used for making this decision, right? The meaning of 5%, this is our error rate. So this is our significance level. And if, so it means if we perform this test like 100 times, so on average we expect to make an error in 5% of our cases, in 5 cases out of 100 cases. Okay, so what I've done on previous slide, it was just a T-test. Okay, T-test compares mean between two groups. Now I did ANOVA test on two groups. And ANOVA test on two groups is the same as a T-test, as a two-sample T-test. And that's why I just wanted to show you we have exactly the same p-value as we previously had on the previous slide. So it was 0.2621. ANOVA 0.2621. Now, in this ANOVA, we can extend ANOVA further. We can extend our two-sample T-test on more groups. What was analyzed in a T-test? In a T-test, if we would like to make an inference, so we can assume that we have a population, and this population was partitioned into two groups only. Okay. But at the same time, we are not talking about all classes that Mr. First and Miss Second actually taught, right? So we're talking only about those two classes. So in this case, we cannot expand our inference further. We're talking only about those two classes. And I just wanted to point this out, because population, which was chosen, which was considered, just those two classes. But more generally, we should consider more classes. For example, if you want to make inference about Mr. First performance and Miss Second performance, so in this case, we should consider more classes, or we should consider simple random sample from different classes. And in this case, we are dealing with a more complicated statistical analysis. Third group. So now we come into ANOVA. From Ttest, we expand into ANOVA. So suppose Mrs. Third comes, okay, and she claims that her class performs much better in terms of average number of target slips per person. So, and what would we do? What will we do in this case? In this case, we should proceed with our ANOVA analysis. Here we have data from Mrs. Third, and her class is bigger in this case, and we can see we have much more subjects here, much more data. And by the way, if we're talking about ANOVA and T-tests, in some cases we're talking about balanced and unbalanced designs. In balanced designs, we're talking about the same number of subjects in each group. In our case, we have unbalanced design, so we have different number of subjects in each group. So that's why this is what we see for Mrs. Third. So, okay, so we can calculate mean number of target slips. We calculated it's 4.7, which you remember is below 6 and below 8, what we saw in the other two groups. And estimated standard deviation was 3.9. So our data is tighter to each other. And so I did not present histogram, because you remember our data are not normal. Okay, but we will proceed if our data were not were normal actually, right? And in this case, the distribution of number of target slips in Miss Third class would look like that. Okay. So when they have smaller variability, it means we have a little bit tighter distribution around our mean. And you remember this was Mr. First class, and this is Miss Second class. Okay. Miss Second class was associated with higher variability. Okay. Now, what problems we have with a T-test? If we have three groups, how we can compare three groups? Because what we need to do, if we want to make any comparisons, we should compare two groups. We should choose two groups, right? And T-test in this case can be applied, for example, on a pairwise basis. First group can be compared versus second, first versus third, third versus second. So we have three comparisons in total, right? So it's three different tests. It's not just one test. And we might have different decisions, okay? For example, if we decide to claim that at least one of our groups is different from the others, we can claim it if we see at least one significant result, for example. Okay, but the problem is, you remember that significance error of 5%, which we looked at the T-test? It was 5% error rate. It means, again, 5 errors out of 100 different tests. But what will happen with this type 1 error in this case if we have several comparisons? Okay, so this is what we see. In one case, 29% p-value. Well, far greater than 5%. So it means that there is no significant difference. Comparing second group and third group, p-value is 1.9, which seems to be a significant result, right? So we want to claim that these two groups are different. But later I will show you that we cannot make this claim. And comparing first versus second group, in this case p-value is 26%, so these groups are not different. And here I emphasized this this point here, is that our error rate is not 5% anymore, okay? Because we perform, instead of one, we perform 3 tests. So if our objective would be just to compare only two groups, for example, second versus third group, we could do it. But in this case, first group of Mr. First class should be excluded from consideration at all. In this case, we can keep 5%. But if we have more groups, that's not true anymore. Okay, and here I try to highlight this problem. One test, suppose we have independent tests. If we have 5% error rate in one case, for one test, that's fine. So at 5 times out of 100, we falsely reject the null when it's actually true. Suppose we have two tests. So probability that we are not rejecting null, but we are correct, is 95% given the null is true. In 95% cases, in 95 tests out of 100, we will be correct if our groups are actually not different. But if we perform this test 2 times, right, and in this case, probability of a correct decision goes down, we should multiply those two probabilities to each other. And probability goes down from 95% to 91. It means in 9% of our cases, we will falsely reject the hypothesis that there is no difference between groups. This is what happens if you perform just 2 tests. Let me go down. What will happen if you perform 50 tests? You see? In this case, 95 to 50. In 7.7% cases, we will not reject our hypothesis that there is no difference between groups. But in 92.3% cases, we will reject. So what does it mean? It's actually often happens when you perform many tests on your data. So if you have your data and you perform one test, so we tested one hypothesis, and after you decide, okay, maybe I should look from a different perspective, from second test, third test, fourth test, and more different tests, and eventually you will be able to find something, okay? But there is no reason to claim in this case that your error rate is 5%, because you performed many different tests. Okay. Now back to ANOVA and what is our null hypothesis, which is tested by ANOVA. Our null hypothesis in ANOVA is that means are the same across all groups which are analyzed. This is what we are testing. And alternative hypothesis in this case is that at least one of our groups will be significantly different from others, at least one. But you remember, if you have 3 groups, it can be first group, can be second, can be third, so it can be anything. The nice part about ANOVA is that when we perform ANOVA test, in this case, we are able to keep this 5% significance level. So we are able to restrict our error to 5% only. And here I performed our ANOVA test on 3 groups, because you remember we had right now 3 classes, right? So I took the same data and I performed ANOVA test. This is p-value which I found. P-value is above 5%. So in this case, if I use 5% as a cutoff for making my decision, in this case I fail to reject the null hypothesis that there is no difference, right? So in this case, I cannot show that there is a difference between groups. But at the same time, you remember when we did 3 different t-tests? We saw p-values like around 30%, and one was 1.9%, okay? So if you want to be scientifically strict, we should perform ANOVA test first. And usually what happens, if ANOVA says that there is no difference between groups, in this case, we are not allowed to look in details, okay? Because if you would start looking into details, start comparing one group versus another group versus third group, so we might be able to see some significant results, but in this case, we are not keeping our error rate at 5% level, okay? Even though we saw 1.9%. At the same time, I should tell that in many cases, if we are dealing with a small sample size, it's really difficult to find a significant difference, to prove that there is a significant difference. So what we usually do, well, we proceed with different types of comparisons. But in this case, we are not trying to make any inference. And in this case, our p-value, like 1.9% or something else, is used only for exploratory purposes, but not for making an inference, not for making a decision. Okay? For example, in clinical trials, you should be really careful about this 5% level. But if you're just exploring your pilot data, say, in this case, you can say, okay, because if you're working with your pilot data, you can use your data for producing some hypothesis, for hypothesis generating purposes. Okay? If you see some result, some p-value like less than 2%, what we just saw, in this case, you can say, okay, this is what I saw. I'm not claiming that this is a significant result, but this is a hypothesis. And I can test this hypothesis if I will have larger sample size. So in this case, you can apply for a grant, right? So this is how you can use your pilot data. Okay, let me go ahead. So as I mentioned, ANOVA keeps error rate at pre-specified level. Yes, so and here I just described our inference which we can make if we have ANOVA p-value, whether it's above 5% or it's below 5%. So, and as I mentioned, if it's above 5%, we cannot show difference between groups. If it's below 5%, we can say yes, at least one group is different from the others. Now, how we can describe ANOVA? What is ANOVA? And ANOVA test is actually based on ANOVA model. And this ANOVA model is simple, because in this case we have this small formula. And this y sub ij, this is what we actually observed. This is number of target slips per person. Okay? But we have two indices here, I and j. Index I corresponds to an individual. And index j, oh, I'm lying, excuse me. I corresponds to our group, to our class. And index j corresponds to individual within this class. So what this model says? This model says that each observation is actually a combination of three different factors. Okay, it's mu, which is overall mean across all groups. So it's average number of target slips across all three classes. But after that, because we know that there is some differentiation, right, from one class to another class, and we need to describe it somehow. In this case, we can say that alpha 1, it would be this difference between our overall mean and what we observe in our class. For example, overall mean across all three groups might be equal something like 5.5 or so. But in first class, in Mr. First class, we saw that mean was equal to 6. In this case, this alpha level can be estimated as 1, right? Alpha 2, it's this difference. It's like effect of second class, which shows how different our second class from overall mean across all three classes. Okay? And alpha 3 corresponds to our third class. So what we observed, again, is right now a combination of three factors. Grand mean across all classes, plus effect of this particular class, and this epsilon sub ij, it's error. Because in one year you can observe one number of target slips per person, another year, another number of target slips, and so on and so forth. Right? So in this case we have some error which is trembling around those mu plus alpha sub I. And yeah, and I described it over here. And this error in ANOVA model, we assume that this error, so this trembling is the same for every individual in our data set. And in this case, we are talking about so-called homogeneous data, because we assume that this variability is similar. In some cases, if our data are not homogeneous, but heterogeneous, so what it means? It means that in one group, we have one variability, but in another group, variability of this study of sleeps might be pretty high. For ANOVA, it's important to have homogeneous variability. Otherwise, some other models should be applied. It was an assumption. Yeah, so, and here I just described, I already described what this model is. So our actual observations, this is what we are not observing because we don't know exactly this means, but we are estimating on our data. So for example, mu can be estimated as just overall average across all three classes. Okay. Now, if we want to apply ANOVA, the problem is we have three classes, but in that model which I showed to you, we had mu, alpha 1, alpha 2, and alpha 3, 4 parameters to estimate. So how to handle this problem? Usually, statisticians specify one of these groups as a reference group, which means that one of our parameters should be set equal to 0. For example, if we say alpha 1 equal to 0, so it means that our mu parameter, it's not mean across all these groups, but mu corresponds to this particular group, group number 1. And in this case, alpha 1 will be difference between group number 1 or alpha 2. Alpha 2 will be difference between group number 1 and group number 2. Alpha 3 is a difference between our reference group, which is group number 1, and group number 3. Okay? So, and in this case, mu represents mean number of tardy sleeps in Mr. First class. And if you remember, it was 6 or so, right? Next step, so mu plus alpha 2 is a mean number of tardy sleeps for Miss second class, and for third class we have mu plus alpha 3. So essentially we have 3 means of 3 groups. This is what we will be comparing in this group. What should we do with our null hypothesis in this case? In this case, our null hypothesis that there is no difference between 3 groups corresponds to what? Corresponds to the situation where alpha 2 and alpha 3 are all equal to 0. So there is no difference between what we observe in first group, second, and in third group. And in this case, this is what we assume. This is what our model is. Under null, under assumption that there is no difference between groups. Okay, because you see, you remember in this I had mu plus alpha 2, alpha I, but if all of those guys equal to 0, so there is no reason to add them up. Alternatively, if our groups are different, in this case we will have to estimate all of those parameters, right? And in this case, we have a little bit more complex structure. In this case, we will get those parameters alpha sub I. ANOVA model, as many other statistical approaches, are based on some assumptions. And these assumptions can be assessed if we use just different plots. For example, you can look at scatter plot. How many classes I had? 3. So in this case, I have 3 groups. Group 1, group 2, and group 3. Okay? In first group, number 1, second, number 2, third, number 3. Okay? And here I just plotted whatever number of tardy sleeps I had in my data set. It's a useful plot just to see what's going on in our data. Okay? So what we can see here is that essentially variability is pretty much close, but might be we will have some outliers. Okay? So you see some observations actually fall a little bit away from the other, from the whole group, right? This is what we see in our data. But at the same time, there is a small problem here, in that suppose we have several zeros, right, in one group. In this case, all these several zeros will be reflected in just one dot, one point on this picture. Okay, so in this particular case, it's not extremely useful way to look at your data. Another way is to build so-called box plots. If any of you previously seen box plots, you probably know that box plots is a representation of 5 numbers. So here we have not mean but median. Median. Here we have maximum, minimum number which was observed in our group. And here we have 25 percentile. And these guys, these are possible outliers. Okay. So this is what can be done if you want to look at your data and try to figure out what's going on in this data. For example, what we can see, if you try to exclude those guys as outliers, so in this case, probably our variability in third group will be smaller, right? And this is actually a violation of ANOVA assumptions, because in ANOVA we assume that we have a homogeneous sample, that variability within each of our groups will be approximately the same. But this is an example of this violation, especially if we exclude those guys, those outliers. Okay. Of course, there are some statistical tests which allow you to compare these variances among groups, but we are not going to analyze it. This is just an example of what's going on in our data. This is another plot, because what we also assume that our data came from a normal distribution. You remember, because this epsilon sub ij supposed to follow this bell-shaped curve. Well, statisticians can visually look at this data if we use so-called QQ plot. Well, the idea of QQ plot that if our data, if all these observations on QQ plot is on a straight line, on a linear trend, so in this case, our data probably came from a normal distribution. In this case, we can see there is some violation here. Okay, so our data is not exactly normal. There are probably some outliers and our heterogeneous data, so no way I should use Ttest here, right, or ANOVA test. But for illustrative purposes, I think it's a good idea just to show it. Okay, so what can be done if our data are, if there are some violations of those assumptions for ANOVA model? So not much can be done actually, and one possibility is to perform so-called outcome transformation. For example, in our data we had 0, 1, 2 and so on number of tardy sleeps, right? But if you use log transformation, for example, in this case our data would be a little bit different from what we saw. But in this case you will be analyzing a little bit different outcomes after this transformation. So you can apply some transformation to your data and compare those transformed data, means of those transformed data between different groups. So, and another way to prepare your data for ANOVA is to exclude outliers. But you see, as only you see some outliers, so some weird observations, you need to justify, and not necessarily in statistical terms, why this or that observation is significantly different from the rest of the group. Okay. For example, suppose some students live outside school attendance area and they need to have a ride to get to the school, so it might be associated with higher number of tardy sleeps. So in this case you can claim that this is an outlier and this is why we see this outlier, and in this case you can exclude it. But this justification can be automatically incorporated in your definition of population. What are you analyzing? Okay? Because if you try to exclude outliers, you need to decrease your population to have a little bit different description for your population that you're analyzing. Okay. So ANOVA, I think we already seen this result. So the same 5%. But here what we can see, it's actually different cutoff values. Because I know that statisticians like this 5% level since Fisher times. But at the same time, in different subject areas, different cutoffs are used to show significant results. Okay. For example, here we can see if our p-value, whatever we observe here, is located between 0 and 0.001, So in this case, we would see 3 stars, which means highly significant result. If our p-value is located between 0.01 and 0.01, which corresponds to 1%, from 0.1 to 1%, we would see 2 stars here. 3 stars corresponds to p-value, which is located between 1% and 5%, and we can see dot here, right? It means that our p-value is located between 5 and 10%. So sometimes people are not very picky about 5%, but we can look at these stripes of highly significant results, less significant, significant, marginally significant, and those which are greater than 10% are not significant at all. Okay? But in many cases, this is used primarily for exploratory analysis, when you see all these p-values and you want to make some interpretation of those numbers. Population, again, we already talked about it. We have 3 groups right now. Wow, that's a complex slide. But this is what we statisticians usually see, and this is what we should make interpretation about. So if we decide that we had a significant result, suppose 5%, 5.3, whatever our p-value we saw, suppose it's a significant result because it's less than 10%, right? What is our next step? Because if we say that there is a significant difference, it means at least one group is different from the others. But our next step is to show which one is different. And in this example, I just made these comparisons. You remember those alpha and mu's which I presented in my model, right, in ANOVA model? And this is what we see in this output. 6.06, it was overall mean. I'm lying, excuse me. It was group 1. It was group 1, right? Because mu was group 1. Now, next group, group 2, was a little bit different, right? And what this difference is? This is this difference, 2.2. So in group 2, on average, we have 2.2 target slips more. If you look at group 3, but again, this number is comparing to group 1. If you're talking about group 3, we have a little bit smaller number of target slips, and this difference is minus 1.3, right? So, and these numbers allow us to justify, to explain what's going on between groups if we see some significant result. So what these p-values tell us? This p-value tells us that there is no difference between group 2 and group 1. This p-value will tell us that there is no difference between group 3 and group 1. Okay? So, and these tests essentially associated with our alpha parameters. After that, what we could compare? We could compare also group 2 and group 3. This can be done in different ways. For example, you can just change reference group. For example, in this analysis, I set group 1 to be my reference group, and I will be comparing the other groups versus group 1. Similarly, I can say, suppose group 3 is my reference group, and I will be comparing the other groups versus group 3. This is just one trick how we can compare group 2 versus group 3. Okay. Yes, so, and here I just mentioned that one more hypothesis can be performed there, so group 2 can be compared versus group 3. So, as only ANOVA test said that there is difference between groups, we actually, after that, as I said, we should compare different groups to each other. But here we are bumping again in these significant results. Which p-value is significant and which is not. And there are many ways how we can describe those. How we can, many different statistical approaches to this problem, to problem of multiple comparisons. And I'll mention just simplest one. It's so-called Bonferroni correction. If you perform 3 tests, it means that alpha level, our significance level, should be divided by 3. For example, suppose our error rate was 10%. If we divide by 3, so if p-value is below 3.3, in this case, we can claim that we found a significant result. Okay? But this is not a subject for this particular lecture, multiple comparisons, because it's much more complex than that. This is just one simple solution, Bonferroni. And here I have a summary for one-way ANOVA, because we talked so far about one-way ANOVA. Our population was split into 3 classes, right? 3 groups, but we had only one factor here. Okay, so one variable, it's class 1, class 2, or class 3. Okay. Second assumption, another assumption, is that we assumed that our noise, you remember this epsilon, follow a normal distribution. And last one, we assume that our variances are approximately the same across all 3 groups. It's homogeneity assumption. Let me just, I have like 10 more minutes, and I'll quickly go over two-way ANOVA. So, suppose Ms. Second says that her number of target slips are even maybe a little bit higher than in the other 2 groups, but it's due to different school attendance area. Okay, so in this case, we got another factor for our analysis. In addition to just group participation, just class participation, we have attendance area. That's another way to partition our population. Okay, and this additional variable can also be incorporated in our analysis. So to this end, we will be talking about two-way ANOVA. Two-way, it means we will have 2 factors. One factor, partition between classes. Another factor, partition all our population between 2 groups. Attendance, school attendance area, and outside the school attendance area. Okay, I mentioned that. And here is our model, which is a little bit different from what we saw before, but the idea is the same. Alpha is for our classes, it's one factor, and beta, it's another factor. It's our school attendance area. Suppose we have just within school attendance and outside school attendance. So in this case, we are only 2 levels in second factor. Okay? Class effect and attendance area effect. So this is how we statisticians usually call it. And if we perform ANOVA, we will have 2 p-values right now. For each of these factors, we will have its own p-value. For example, first p-value stays approximately the same, okay? And second p-value, which corresponds to the school attendance factor, is about 50%. It means that there is no effect from school attendance area, okay? Yeah, and here I showed how we split our population. So one factor splits into 3 pieces by classes. Another factor slices into pieces, right? All our population. So outside school attendance and inside school attendance area. Yep, and that's it. If you have any questions, I'm happy to answer.